Welcome to module 1 of chapter 2. In this chapter, we will define what are prime numbers, composite numbers and congruences. We will prove one of the important results of number theory like fundamental theorem of arithmetic, Fermat's little theorem, Wilson's theorem and then Chinese remainder theorem. In this module, we will define prime numbers, composite numbers and prove fundamental theorem of arithmetic. Chapter 2. In the chapter 2, we are going to discuss prime numbers and congruences. So, in the module 1 of this chapter, we are going to discuss primes and their properties. So, the objectives of this module are prime numbers and composite numbers and their properties, and we will state and prove fundamental theorem of arithmetic. So, first we will define what is a prime number. An integer p is said to be a prime if p is greater than or equal to 2 and only prime divisors of p are 1 and p. So, here we are assuming that for positive integers we are defining concept prime for only for positive integers. So, we are assuming an integer greater than or equal to 2 is said to be prime if the only positive divisors of are 1 and itself. So, an integer n is said to be composite if n is greater than or equal to 2 and n is not a prime. If you look at the definition carefully, both the cases for prime as well as for composite, we are assuming that that number is greater than or equal to 2. Okay. So, that means we are defining only for the positive integers. So, a number 1 is neither prime nor composite. Since we are assuming prime or composite both are greater than or equal to 2, so clearly 1 is not a neither prime number nor composite number. Even for negative side, for negative integers also, if for example, if p is a prime, we can extend that idea to minus p as well. That means 5 is a prime number, minus 5 is also considered as a prime number, but in this module we are just considering prime means a positive integers. So, an integer n greater than or equal to 2 is composite if and only if there exist integers a and b such that n is equal to a b and 1 less than a less than n and 1 less than b less than n. So, this is if and only if condition. It is actually the definition also says this, means a number is composite means it is a not prime number, that means it has a divisor which is other than 1 and itself. So, automatically once it has a divisor which is other than 1 and itself, then other divisor also need to be licensed between 1 and itself. So, that is what this lemma says. So, we will use this without later frequently. Let n is greater than or equal to 2. If n is a composite, there is a positive integer a such that a is not equal to 1, a is not equal to n and a divides n. This means that n is equal to a b for some b. Since n and a are positive, so is b. By definition, 1 is less than a is less than n and so b is greater than or equal to 1 and less than or equal to n. If b equal to 1, it is clear that a equal to n. This is not possible since a is strictly licensed between 1 and n. So, b is not equal to n. Similarly, if b equal to n, we have a equal to 1, that is also not possible. So, b should be strictly licensed between 1 and n. So, converse is quite obvious since once we have that n is equal to a b and a and b licensed between 1 and n, then clearly n is composite. Next, we will prove another result that if n is greater than or equal to 2, then there is a prime p such that p divides n. We will prove this result by induction on n. The result is holds for n is equal to 2, since 2 itself is a prime number, it divides itself. So, let us now suppose that result is true for all integers n less than k. That means, here we are using principle of complete induction, not principle of mathematical induction. We are using complete or strong induction. Let n equal to k. If k itself is prime, then we are done. Else k is composite. Hence, there exist integers a and b such that both a and b strictly licensed between 1 and k equal to a b. So, this just followed from the previous result. So, we have k equal to a b and a and b licensed between strictly licensed between 1 and k. So, what happens now both A and B are divisors of K. Now, I apply induction for hypothesis on either A or B, then we will get the required result. It is because both A and B greater than 1. So, both are greater than or equal to 2. So, we will get the required result. So, what we proved is if n is greater than or equal to 2, then there is a prime such that p divides that number. So, every number greater than or equal to 2 has a prime factor. Now, we will prove another result. If n is greater than or equal to 2 is a composite number, then n has a prime divisor p which is less than or equal to root n. The proof is very simple, that is let assume that n is greater than or equal to and a composite number, then n is equal to a b, where both a and b strictly lies in between 1 and n. We claim that one of a and b is less than or equal to root n. In fact, we are claiming more. Actually, we need to show that there is a prime which divisor which is less than or equal to root n, but we are proving that one of the divisor itself is less than or equal to root n. So, what happens if it is not true? That means, if assume that a is greater than root n as and b is greater than root n, which implies that n is equal to a b, which is greater than root n into root n, that is equal to n, which is a contradiction because we are getting n is greater than n. So, a is less than or equal to root n or b is less than or equal to root n. Suppose a is less than or equal to root n. Since a is greater than or equal to 2, there is a prime p such that p divides a. This follows from the previous result. Hence, p divides n. So, hence we have a prime divisor p for n such that which is less than or equal to root n. So, this is an important result to check whether the given number is composite or prime. So, theorem helpful in deciding whether an integer is a prime or not. To check whether or not n greater than or equal to 2 is prime, we only need to divide n by all primes p less than or equal to root n. If none of these primes divide n, then n must be a prime. So, we will state this as an algorithm, but before that we will see an example. Consider the number 89. If you look at that, root 89 is less than root 100, it is equal to 10. So, the primes less than or equal to 10 are 2, 3, 5, 7. So, one can easily check that none of the primes 2, 3, 5, 7 divide 89. So, from that previous result 89 is a prime number. So, we will translate this into an algorithm. So, in the algorithm the input is this, an integer which is greater than or equal to 2. We want to check output is, we want to check whether it is a prime number or not. So, first we will list all the primes less than or equal to root n. If any one of them is a factor of n, then n is not prime. We will stop the algorithm. We will conclude that n is a composite number, else n is prime. So, the algorithm is very simple, just we need to check that we list all the primes less than or equal to root n, and we need to check at least one of them is dividing n or not. So, now we will go to important lemma called Euclid's lemma. What it says is, if the GCD of a comma b equal to 1, then a divides bc, then a divides c. This is one of the important results we will use very frequently. So, I request you to remember this statement. Here important thing is GCD of a b equal to 1 and a divides bc, then we will conclude that a divides c. So, how to prove? Since GCD of a comma b equal to 1, then by Bezoart's identity there exists x comma y such that 1 is equal to ax plus by. Thus, if you multiply both sides with c, you will get c is equal to acx plus bcy. Also, this in the hypothesis it is given that a divides bc. So, bc equal to az for some z belongs to z, that is an integer. Hence, c is equal to acx plus bcy, but bc is equal to a into z. So, if I plug in bc value there, so I will get this equal to a times cx plus zy. So, c is a multiple of a. So, hence a divides c. Now, it is important corollary of this Euclid's lemma is this, which is very useful, that let p be a prime and p divides a b, then p divides a or p divides b. The proof is straightforward. So, if we have if p divides a, then we are through. what we have to show, P divides A or P divides B. So, if P divides A, then we are done. If P does not divide A, then what it means? GCD of P comma A becomes 1. It is because the only divisors of P are 1 and P. So, GCD of P comma A is a common divisors of A and B. So, only common divisor is 1. Hence, from Euclid's lemma, we have that P has to divide B. Since P divides A B, it is given. Now, GCD of P comma A is 1. So, P has to divide B. Note that in the above result is not true when P is not prime. For example, 6 divides 2 into 3, but 6 does not divide 2 and 6 does not divide 3. This result can be extended, that is, if let P be a prime and P divides A1 A2 An, then P divides A for all I, where 1 is less than or equal to I is less than or equal to n. So, this result can be proved by induction or any other means. We will proving by induction, the induction on the number of factors in that product, that is A1, A2 and so on An, there are n products, n factors. So, n equal to 1, the result is clearly true. Suppose the statement is true for all k less than n, then that is, if now if we assume P divides A1 A2 An, then from the corollary we saw that P divides A1 or P divides A2 A3 and so on An. That means A1 into A1 A2 An we divide it into two product of two numbers A1 and A2 A3 and so on An. If P does not divide A1, then by induction hypothesis P divides A for some I which is lies in between 2 and n. Hence, result follows from PCI, principle of complete induction or strong induction. Now, another corollary is that if P is a prime number and P divides A, then it is easy to show that P power n divides A power n. And another lemma, if let A, B, C are integers and GCD of A comma B C equal to 1, if and only if GCD of A comma B equal to 1 and GCD of A comma C equal to 1. So, the proof is again straightforward. Suppose that GCD of A comma B C equal to 1, we have to show that GCD of A B equal to 1 and GCD of A comma C is also equal to 1. If GCD of A B equal to D, then by definition of GCD, D divides A as well as D divides B, thus D divides B C. So, D divides GCD of A comma B C, that is equal to 1, hence D equal to 1. Similarly, we can prove that GCD of A comma C is also equal to 1. Conversely, we can suppose that GCD of A comma B equal to 1 and GCD of A comma C equal to 1, then we have to show that GCD of A comma B C is also 1. So, we will prove by contradiction. If we assume GCD of A comma B C equal to D, which is greater than 1, then just now we proved that every number greater than or equal to 2 has a prime factor. So, D has a prime factor, let us say P. So, since D divides A as well as B C, so P has to divide A and B C. So, again P divides B C implies P divides B or P divides C. Thus, P divides GCD of A B or P divides GCD of A C, it is a contradiction, as GCD of A B equal to 1 and GCD of A C equal to 1. One of the important problem of number theory is that we need to find given number is prime or not. So, just now we saw an algorithm which evaluates whether given number is prime or not, but one of the problem is that algorithm is that in order to know whether that number is prime or not, we need to evaluate all the primes up to root n, and we need to see that whether at least one of these primes divides n. But if as n becomes large, root n itself is very large number. So, it is this takes an exponential time to check whether given number is prime or not. So, though theoretically we have an algorithm, but this is not used for practical purposes. This is useful only when the number is very small. So, now another interesting property we saw for prime numbers is that if P divides A B, then P divides A or P divides B. This is one of the nice feature for prime numbers. In the later, in higher studies, we will use this as a definition for defining a prime. That means, P divides A B, then a number is said to be prime if P divides A B, then P divides A or P divides B. And we proved this result, that P divides A B implies P divides A or P divides B by using Euclid's lemma, just recall what Euclid's lemma says. Euclid's lemma says that if the GCD of A comma B equal to 1 and A divides BC, then A has to divide C. This we use to show P divides AB implies P divides A or P divides B. Now, we are going to see one of the important result in number theory called fundamental theorem of arithmetic. Now, we will prove one of the important result in number theory, that is fundamental theorem of arithmetic. The statement is every positive integer greater than 1 can be expressed as product of primes, and this representation is unique. Unique in the sense that apart from order in which the factors occur. Okay, we will repeat because of its importance. Every positive integer n greater than 1 can be expressed as product of primes. This representation is unique apart from the order in which the factors occur. Now, we will prove this result. So, we will go step by step. So, if n itself is prime, then we are done, nothing to prove, that is expressed itself, that is n equal to n into 1. If n is composite, then we define a set Sn is equal to d belongs to z plus, that is positive integer, d is a positive integer, and d is a divisor of n, and d is Lyson between 1 and n. This is true because we are assuming n is composite. So, there is a divisor which is strictly Lyson between 1 and n. So, this Sn is non-empty, and further we are assuming all these integers are positive. So, Sn is a non-empty subset of positive integers. So, obviously, whenever we come across this, then we will recall well ordering principle. So, by well ordering principle, Sn has a least element. So, let us say that least element is P1. Now, we will claim that P1 is prime. So, it is nice to see the proof of that one as well. So, if for example, if P1 is not a prime number, then what happens? Since P1 is greater than 1, that means P1 is greater than or equal to 2. So, every number greater than or equal to 2 has a prime factor, that result we proved earlier. So, because of that what happens, P1 is equal to again product of two integers A and B. So, that means that, and both A and B again Lyson between 1 and P1. So, at least it has one divisor which is Lyson between 1 and P1. So, that also divides n, that means we have produced another integer which is less than P1 and divides n. So, which is a contradiction for minimality of P1. So, that is the reason P1 has to be prime. So, well ordering principle providing us the least element itself is a prime number. So, we have n is equal to n1 into P1, where P1 is the smallest prime dividing n, and n1 is strictly Lyson between 1 and n. If n1 itself is a prime, then we are done, that means we expressed n as a product of primes, n1 is a prime and P1 is a prime, we got the required representation. There is a possibility that n1 may be equal to P1, that is not ruled out. So, but even then we got n as a product of primes. Now, otherwise, that is, if n1 is not prime, then what happens? We will now consider Sn1, as we constructed Sn, like that we can construct Sn1. So, the smallest element in this Sn1 now is P2, and again with the same argument P2 becomes a prime. So, we have n is equal to P1 into P2 into n2. So, now again if n2 is prime, then we are done, that n is equal to product of primes. If n2 is not prime, then what we have to do? Again we will consider another set Sn2 that contains all the divisors which are Lyson between 1 and n2. Again we will repeat the process, that is, if n2 is not a prime, then we will proceed as the same. One can easily notice that Sn1 is a proper subset of Sn, thus we will get a decreasing sequence, n is greater than n1, greater than n2 and so on, or this is also we can state in a different way, that is empty set is contained in and so on, that Sn is the largest set here, it contains Sn1, Sn1 contains Sn2 and Sn2 contains Sn3 and so on. Since the number of divisors of Sn is finite. So, this we cannot continue indefinitely. So, this process has to terminate. So, after finite number of steps, say, then what happens, Sn1 Sn minus 1 becomes a prime, say Pk. Hence, n is equal to P1 into P2 into and so on Pk. So, now we are ready to prove the uniqueness. Just now what we proved is n is a product of primes. Now, we will go for uniqueness. So, if you look at the proof till now we done, one can argue that the proof itself is saying that uniqueness directly follows, but that is not the idea. What happens, different people can prove the results in different ways. So, it is necessary for us to prove uniqueness as well. Now, let us assume n has two prime representations, that is we are assuming that n equal to P1 into P2 and so on Pr, as well as which is also equal to Q1 Q2 and so on Qs. Then we have to show that these two P1 is equal to Q1, P2 is equal to Q2 and so on, Pr is equal to Qs, and of course, obviously we have to show that R equal to S. So, our objective is that these two, all these primes are equal. So, for that, for assume that R is less than or equal to S, where Pi, Pj are primes written in increasing order, that is we are also assuming order, that is P1 is less than or equal to P2, less than or equal to and so on Pr, Q1 is less than or equal to Q2 and so on, less than or equal to Qs. Now, our objective is to show that P1 is equal to Q1, P2 equal to Q2 and so on, Pr equal to Qs. So, let us see how we will proceed. Since P1 divides P1 into P2 and so on Pr, so P1 divides Q1, Q2 and so on Qs. So, the from the conditions of primes, that is P divides A B, we know that P divides A or P divides B. So, we can easily check that P1 has to divide one of these Q1, Q2 and so on Qs. So, let us assume that P1 divides Qk. Since these are all primes, P1, P2 and so on Pr are primes, Q1, Q2 and so on Qs are primes. So, P1 has to be equal to Qk for some k from 1 to S. Now, again there is an ordering in Q1, Q2 and so on Qs. So, since Qk is greater than or equal to Q1, so P1 is greater than or equal to Q1. So, similarly with similar argument, that means by proving by taking Q1 divides P1, P2 and so on Pr, we will end up with Q1 is also greater than or equal to P1. Thus, we have P1 is equal to Q1. So, now in the above expression, that is n is equal to P1, P2 and so on Pr, which is also equal to Q1, Q2 and so on Qs. Since P1 is equal to Q1, we can cancel those two. So, we will get P2, P3 and so on Pr is equal to Q2, Q3 and so on Qs. That is P2 into and so on Pr is equal to Q2 and so on Qs. By continuing in this process, we can show that P2 is also equal to Q2, implying P3 and so on Pr is equal to Q3 and so on Qs. So, if you repeat this process, what happens? We need to have R is equal to S. It is because since Q1 is equal to Q1, P2 equal to Q2 and so on, Qr is equal to Pr is equal to Qr. On the contrary, if we assume that R is less than S, then we will eventually arrive at 1 is equal to product of primes like Qr plus 1 into Qr plus 2 and so on Qs. Product of primes never be equal to 1. So, this is a contradiction. So, we have R is equal to S, and automatically we have that P1 is equal to Q1, P2 equal to Q2 and so on, Pr equal to Qr as well. So, with this we proved the uniqueness part as well. So, we proved the fundamental theorem of arithmetic. Now, we will show that if n is equal to P1 power k1 and so on, Pr power kr is a prime factorization of an integer n greater than 1 into distinct primes, then any divisor of that n is of the form P1 power a1, P2 power a2 and so on, Pr power ar, where ai's are licensed between 0 to ki. So, we are giving prime representation for all its divisors of n also. Once we know the prime factorization of n, it is possible to know prime factorization of all its divisors. So, we will go case by case. First observe that if d equal to 1, then all a is equal to 0. So, we are done. If even if n is if d is equal to n also, it is easy to see all a is equal to k I. If d is a non-trivial divisor of n, that is d d1 is equal to n, since we have n is greater than d, so d1 should be greater than 1. So, now let us take d equal to T1, T2 and so on T A be the prime factorization of d, and d1 is equal to S1, S2 and so on S B as a prime factorization for d1, then their TAs and SJs need not be distinct, they are just prime factors of d and d1 respectively. Then we have that since d into d1 is equal to n, so p1 power k1 into p2 power k2 and so on pr power kr, which is equal to T1, T2 and so on Ta into S1, S2 and so on into Sb. Two distinct prime factorizations for the positive integer n, but we proved that every positive integer greater than 1 can be expressed as product of primes uniquely. So, these two representations will help us to say that the T1, T2 and so on Ta, S1 and S2 and so on Sb are going to be one of these primes P1, P2 and so on Pr. That is, so collecting all equal primes into single integral power, we will get d is equal to T1 into T2 and so on Ta. So, which is going to be equal to P1 power A1, P2 power A2 and so on Pr power Ar, where the possibility of A is equal to 0 is allowed. So, what we proved here is that if you know the prime factorization of an integer n, then it is possible to know the prime factorization of all its divisors. All its divisors also have prime factors, one of the prime factors from the n itself. So, now the converse part is easy. So, conversely, if you assume that d is equal to p1 power a1, p2 power a2 and so on pr power ar, where 0 is less than or equal to a is less than or equal to ki for 1 I equal from 1 to r, then it is easily to see that this d divides n. Now, we will prove another result, that is if n is greater than or equal to 2 belongs to Z, then n can be expressed in the form n is equal to ab square, where a and b belongs to Z and a is a square free. An integer is said to be square free if it is not divisible by p square, where p is a prime. So, all its prime factors are powers are 1. That means, if a equal to p1 power 1 and p2 power 1, both a and b are distinct. Like that, the prime factorization contains only exponents are either 1 or 0. So, now how to prove this result? This is another representation for integers. So, let us take n equal to p1 power k1, p2 power k2 and so on pr power kr. This prime factorization is possible because of the fundamental theorem of arithmetic. Now, what we will do, we will use the division algorithm for k1, k2 and kr, and b will take as 2. That means, if I divide k1 by 2, we will get some remainder say r1. So, like that we are going to get k1 is equal to 2q1 plus r1, k2 equal to 2q2 plus r2 and so on, kr is equal to 2qr plus rr. So, since we are dividing by 2, so the remainders Ra value is either 0 or 1, depending upon either k is even or odd. So, consequently, if you set a is equal to p1 power r1, p2 power r2 and so on pr power rr, and b is equal to p1 power q1, p2 power q2 and so on pr power qr, then we will get the required representation for n. It is because p1 power r1 is either 0 or 1, r2 is either 0 or 1, rr is either 0 or 1. So, clearly a is a square free integer, and now if you square it b square. So, what is a b square value? B square equal to p1 power 2q1 into p2 power 2q2 and so on pr power 2qr. So, product of a into b square is exactly equal to n. Now, if you take n is equal to p1 power a1, p2 power a2 and so on, pr power ar, and also m is equal to p1 power b1, p2 power b2 and so on, pr power br, two integers, then it is easy to evaluate GCD of m comma n. So, here we are not giving the answer, but it is easy to find out what is the GCD of m comma n. So, you are invited to find out this. Also try to find out LCM of m comma n and product of n into m, that is quite obvious. And the proof of LCM of a comma b into GCD of a comma b is equal to ab also becomes easy now with this, once we have a prime factorization for n and m. Now, we also request you to solve these problems, they are easy to solve. The first problem is that the only primes of the form n cube minus 1 is 7, the only primes of the form n square minus 4 is 5. Another problem, let p be a prime with p greater than or equal to 5, then p square plus 2 is not a prime. Here we are going to utilize that division algorithm. So, we know that every integer is of the form 6k or 6k plus 1 or 6k plus 2 and so on 6k plus 5, and 6k plus 2, 6k plus 3 clearly they are not primes. So, the primes has to come from 6k plus 1 or 6k plus 5. So, it is easy to check for these two cases, p square plus 2 is not going to be a prime number. Another problem is, for every integer of the form n power 4 plus 4 is also a composite number. If n is greater than 4 and is a composite number, then n divides n minus 1 factorial. Here we should be little careful. So, you have to understand why we took n greater than 4, and also you have to divide the problem into two cases, that is n equal to p square case and n is not a p square case, and each integer n greater than 11 can be expressed as sum of two composite numbers, and here we given some hint. So, you can proceed with that, and if p is greater than or equal to q is greater than or equal to 5 and p and q are both prime, then prove we have to show that 24 divides p square minus q square. If p is not equal to 5 is an odd prime, then prove that either p square minus 1 or p square plus 1 is divisible by 10. In this module 1 of chapter 2, we studied various properties of prime numbers. We also proved one of the main result of number theory, fundamental theorem of arithmetic. Because of fundamental theorem of arithmetic, prime numbers becomes building blocks of all the integers. We also saw few applications of fundamental theorem of arithmetic. If you know prime factorization of two integers, then it is possible to find their divisors, GCD, LCM, etc. very easily. Finally, note that fundamental theorem of arithmetic is just an existence theorem. Finding prime factorization of a given integer by applying fundamental theorem of arithmetic is difficult. With this we end module 1 of chapter 2.